In this class, I want to explain central limit theorem. Yes, the concept central limit theorem. Very important topic. We write the statement of central limit theorem. Statement. It states that the probability distribution function of a sum of n independent random variables approaches the Gaussian distribution function as n tends to infinity. Okay, let me explain. Yes, let us suppose you have n independent random variables. If you sum all these random variables and if you find the distribution function of this sum, then the distribution function shape is Gaussian. This is the statement of central limit theorem. Okay, so now again here we have two cases actually. Unequal distributions and equal distributions. In unequal distributions, these n random variables are different. These n random variables are having arbitrary probability densities or arbitrary probability distribution functions. The n random variables are different. Okay, then what will happen? Then if you sum those type of random variables which are having arbitrary probability densities or arbitrary probability distribution functions, then the probability distribution function of the sum asymptotically reaches Gaussian. So, in this case, you will get asymptotically reaches Gaussian. I'll repeat. In the case of unequal distributions concept, the n random variables that we consider having arbitrary probability density functions or arbitrary probability distribution functions. So if you sum those type of random variables and if you find the distribution function of that sum, then that distribution function asymptotically reaches Gaussian. Not exactly, it is asymptotically. Okay, so that is the reason we are not having any proof for the case of unequal distribution. Okay, but for the equal distribution, all the n random variables are having equal distribution functions or equal density functions. Equal distribution concept, all the n random variables are of same type, means of having equal distributions. Then if you sum those type of n random variables and if you obtain the distribution function for that sum, it exactly reaches Gaussian. Okay, so that is the reason of having a perfect proof in the case of equal distributions. Okay, so now we'll start it by taking equal distributions concept. N continuous random variables, xn, where n is 1, 2, etc. n. And consider all these random variables are having same distribution. density functions. Let the sum yn equal to, sum is represented by yn, x1 plus x2 plus etc. plus xn. This is the sum. Is it fine? Now, I'll define a random variable, wn, which is of 0 mean and unit variance. 0 mean and unit variance. Let that be represented by wn equal to yn minus yn bar by sigma yn. This is the random variable that we consider. What is your wn? Yn minus yn bar by sigma yn, where yn is, you already know it is the sum sigma, I is from 1 to n xi. And what is yn bar? Mean of the sum, sigma, I is from 1 to n xi bar. Then sigma yn square is sigma, I is from 1 to n sigma xi square. Okay, implies your sigma yn is root sigma, I is from 1 to n sigma xi square. Okay, see here, actually the sum is yn. How to prove actually in the central limit theorem concept? The distribution function of that sum is Gaussian. But here, instead of taking directly the sum yn, we considered a random variable wn, which is of 0 mean and unit variance, that is equal to yn minus yn bar by sigma yn. What is yn? As usual, it is sum. What is yn bar? It is mean. We all know mean is a numerical value. What is sigma yn? Standard deviation, because sigma yn square is variance. So sigma yn is standard deviation. It is also a numerical value. So if you see this wn expression, yn is sum of the random variable, means it is in the form of random variable concept only. But yn bar and sigma yn are numerical. Okay, then what is the nature of wn? It is the nature of sum only. Okay, so that is the reason of considering wn like this. So now your yn is, yes, the sum of your random variables. Yn bar is the mean. Sigma yn square is the variance of the sum. You'll get this by adding or by summing variances of all your random variables. But here in the denominator you have only sigma yn. So that is the reason of taking just root here. We know all the random variables are having same distribution or same distribution. Therefore, you can write xi bar as x bar and sigma xi square as sigma x square. Denominator term, what is the denominator term? Root sigma, I is from 1 to n sigma xi square. That is equal to sigma I is from 1 to n. I'll take the root only for root xi square because it is the summation. So it is root sigma. In the place of xi, you can write x. So sigma x square. Okay. As you are adding this sigma x square for n times, it becomes root n into sigma x square. Because see here, if change the I from 1 to n, it is sigma x1 square plus sigma x2 square. It is under root sigma x3 square, etc. sigma xn square. As all the random variables are same, that sum gives n times of the variance. So that is the reason of taking n into sigma x square here. So it is nothing but root n into sigma x. Therefore, your random variable Wn is, simply substitute all these information into the random variable. Yes, yn and yn bar. Yes, sigma I is from 1 to n, xi, that is the first term, and you have the same sigma here, so take sigma common. And xi bar can be written as x bar because all are having equal distributions, divided by root n into sigma x. Okay. Now you have to show that this random variable is Gaussian. Okay, you have to prove that this is a Gaussian random variable. Wn is a Gaussian random variable. Okay, this is all about the statement under equal distributions. Now let us see the proof. Prove this random variable Wn as a Gaussian random variable. Simply, you have to prove that phi Wn of omega is equal to exponential minus omega square by 2. Let me explain what are these things. What is this? Characteristic function of Wn. What is this? Gaussian form. You have to prove that the characteristic function of the random variable Wn is Gaussian. Okay, that's enough. Okay, let me explain few things. First point, e power minus t square or e power minus omega square or e power minus f square, denominator may be anything or it may have some magnitude like that, whatever may be, but if the exponential form is like e power minus t square or e power minus omega square, e power minus f square, these are all the forms of Gaussian. This is called Gaussian form. Okay, so that is first point. And the second point is Fourier transform of Gaussian is Gaussian itself. That is the next point. The point, characteristic function and density function are Fourier transform pair. These three are very important. And here a small point is characteristic function and density function are Fourier transform pair with negative sign for omega. All these are very important to understand this derivation. Okay, so now let me explain clearly. Fourier transform of Gaussian is Gaussian, fine. The characteristic function and density function are Fourier transform pair. Okay, now you look at this. Characteristic function of the random variable Wn is Gaussian, fine. As the characteristic function and density function or Fourier transform pair. What is the density function shape? Gaussian. Because I already told you Fourier transform of Gaussian is Gaussian. And as the characteristic function and density function are Fourier transform pair, and if we see the characteristic function is Gaussian, so the density function of the random variable Wn is also Gaussian. Okay, so that is our proof. If the density function is Gaussian, distribution function is also Gaussian, then you can say that random variable as a Gaussian random variable. I think it is clear. Okay. Now we continue this proof. Characteristic function of Wn is, according to the definition, expectation of e power j omega into the random variable. Okay, actually the notation is like this: phi x of omega. Phi x of omega equal to expectation of e power j omega x. That is the characteristic function of the random variable x. Here it is the characteristic function of random variable Wn. Okay, in the place of x you simply write Wn. Okay, so what is this? You substitute simply, yes, you write it like exp, then it will be easy. J omega, okay, into what is Wn? Yes, this is the Wn. So now in the denominator I'll keep this, okay, and sigma I is from 1 to n xi minus x bar. Okay, so that is the expression for characteristic function of the random variable Wn. Okay, so now here you have to do one simplification. See, all the variables are independent. Okay, if all the variables are independent, then if you see this expression, inside it, means inside this expectation, you have one sigma. So now if we change the I value from 1 to n, this term becomes x1 minus x bar plus x2 minus x bar plus x3 minus x bar, like this. Means you will get expectation of sum of xi minus x bar. If the random variables are independent, another important point is, if you have x1 plus x2 plus etc. plus xn, if these random variables are independent, then this is equal to e of x1 into e of x2 into e of xn. Okay, and all these random variables are same. Okay, so then e of x into etc. e of x. So it will be of x whole power n. Okay, this is also very important point. Yes, use this notation here. So now it will be, this is expectation of sum of xi minus x bar. So it becomes multiplication of their expectations, and all the random variables are same. So the multiplication is for n times. So it becomes the power as it is multiplication. So it is power n. Okay. Now we have to use Taylor's polynomial. What is Taylor's polynomial? E power x equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Now using this Taylor's polynomial, you have to expand this exponential term, then apply expectation, then apply power n. Then you are going to get 5 Wn of omega. Okay. Then using Taylor's polynomial, you can write expectation of exponential of j omega by root n sigma x into xi minus x bar as, first I'll write this, after that I'll take the power n. Is that okay? So that is equal to expectation of Taylor's polynomial 1 plus e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. So 1 plus, what is x here? This is all x here. So j omega by root n sigma x into xi minus x bar plus j omega by root n sigma x xi minus x bar whole square divided by 2 factorial plus etc. Write the term Rn by n. Okay. So now you apply expectation on all the terms individually. Okay, see here, the remaining terms are totally considered as Rn by n, where Rn by n is remainder term. This is remainder term. Remainder term. Okay, so now if you apply one by one, so it is, first term is e of 1 plus j omega by root n into sigma x expectation of xi minus x bar plus 2 factorial is 2, so 1 by 2, j omega by root n sigma x whole square is there, so it is minus omega square by n into sigma x square into expectation of xi minus x bar whole square. This is all constant, na? So next is expectation of Rn by n. Is it okay? And we know expectation of 1, expectation of a constant is constant, plus j omega by root n sigma x expectation of xi minus x bar. So I explained this expectation of xi minus x bar in the case of properties of expectation concept. Okay, it has already video, just verify. Expectation of xi minus x bar is x bar minus x bar omega square by 2n sigma x square into, what is this? This is nothing but variance. So it is sigma x square plus expectation of Rn by n. So it is 1 plus, it is 0. Okay. And here sigma x square gets cancelled. Okay. So this is 0 now. So 1 plus 0 minus omega square by 2n plus etc. plus e of Rn by n. And this e of Rn by n tends to 0 if n tends to infinite. Can be applied only if the number of random variables is very high. That n must be very high. Then only you can prove that the distribution function of the sum is Gaussian. Okay. So then what is totally this? Therefore, expectation of exponential of j omega by root n sigma x of xi minus x bar is equal to, yes, total it is 1 minus omega square by 2n. But characteristic function of Wn is, what is this? Expectation of exponential of j omega by root n sigma x xi minus x bar whole power n implies characteristic function phi wn of omega is equal to, yes, in the place of this inside term you simply substitute 1 minus omega square by 2n whole power n. Apply natural logarithms on natural logarithm on both sides. We'll get ln of phi wn of omega is equal to, if you apply ln here, this power becomes multiplication n into ln of 1 minus omega square by 2n. Okay, now consider another identity. Ln of 1 minus z is equal to minus of z plus z square by 2 plus z cube by 3 plus etc. when mod z is less than 1. Definitely. Okay. Now use this identity for this term. So here the z is omega square by 2n. And verify whether mod z is less than 1 or not. Is definitely less than 1 because in the denominator you have 1 which is of very high value. Okay. So then by using this identity you can write this ln of phi n of omega is equal to, yes, n is here and minus is here. So minus n of, what is z? Omega square by 2n. What is z square by 2? 1 by 2 into omega square by 2n whole square plus etc. Okay. So now just multiply it with n. N gets cancelled. Here is n and here is n square. So you have n in the denominator for this term. And the central limit theorem is for n tends to infinite. So if n tends to infinite, in the denominator you have n. So this term becomes 0. So it will be with only minus omega square by 2. So what is this? ln of phi wn of omega. Okay. Now you take ln on this side, it becomes exponential. So implies your phi wn of omega is equal to exponential of minus omega square by 2. Okay, see here, we proved the required thing. Yes, okay. So what is the first statement of our proof? You have to prove that the characteristic function of your random variable wn is equal to exp is equal to e power minus omega square by 2. Okay, so that is the first sentence of our proof and here we proved it. Okay, so now what is this characteristic function of your random variable? As the characteristic function is Gaussian, it implies, what it implies? The density function of Wn is also Gaussian. If it is Gaussian, distribution function is also Gaussian. Okay, only for the Gaussian case it happens. If the density function is Gaussian, distribution function is also Gaussian, because integral of e power minus t square consists of e power minus t square term. Again, differentiation of e power minus t square term is also consists of again e power minus t square term. Okay, so this is the proof for central limit theorem in the case of equal distributions. Okay. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.